with all the participants. If anybody has any objections to this webinar being recorded, let us know now. Okay, so I don't hear any opinion. So while this is a webinar and you are all having access to participate, we would probably request that for questions we would you can raise your hand, and Charlotte or myself, we would call you to ask your questions. You are also welcome to type questions in the chat window, and we can read them out. So the agenda, as I've shared here, we will be going through some presentations. You can have the opportunity to ask a few questions at the end of each presentation. But if there are more questions and if there needs to be more discussion, then it could be done at the end of this webinar, where we have a lot of time for more discussion. Without then further delay, I think we can start the webinar now. I think we will probably have more people joining as we go forward, which is perfectly fine. I think we will also have the rule that all of you should please put your mobile phones on silent if that's possible. I don't know what the bandwidth of all the internet is for everyone, so it would be good if the speaker or the presenter has his or her video on, while everybody else has their video off and is on mute. That would be good for having a smooth presentation. And each of the speakers can individually share their presentations as they are making the presentation. So then I will stop sharing. And as the first item on the agenda, I would like to welcome Mr. Loic Blanchard, who's a project officer for the Hyperwind project from the European Commission. I would like to welcome him and ask him to make a presentation about the Hyperwind project and how the European Commission sees the current project as well as the Horizon Europe objectives. Thank you.
Thank you very much. I don't know if you can hear me correctly.
Yes, we can hear you.
You can see me, hopefully.
Yes.
Okay. Yeah, well, good afternoon, everybody. Thank you for the invitation. Special thanks to Anand from DTU. I'm very glad to be here with you. I mean, only online. It's, well, would have been better physically, but travel restriction being what they are. What I'll do today is, I don't know if should I put up my presentation or?
Yes, if you can, then that is fine. Or if you would like that we share your presentation.
You can share the presentation. Yes. If you don't mind, can share it. Then after you'll be able to also share it with the participant afterwards.
Yes. So I am sharing now. I think I'll put it on full screen mode.
Good. Thank you very much. So what I'll do today, I mean, in 10 minutes, not more, is to give you a short overview of CINEA, the Horizon Europe programs, and where wind power fits in the Horizon Europe program in the next 2 years. So, as Anand said, my name is Loic Blanchard, and I'm a project manager in CINEA in sector renewables. So, next slide. What is CINEA? I mean, it's an acronym for European Climate, Infrastructure, Environment Executive Agency. Is a bit long, but is in fact a successor organization of a former agency that you might know, which is INEA, that has been merged and has started to work in April. And these agencies in charge of implementing different programs that would support the EU Green Deal, which is the key EU objective for the next 10 years. So our role is managing programs. We can go to the next slide, where you have the different programs. So we have legacy program, but we also have new programs. You can see them on the slide, which is, it's a bit broad. You have the Connecting Europe facility, which has those large-scale infrastructure projects within member states. We have a new instrument, which is the Renewable Energy Financing Mechanism, which is an instrument that aims to develop a cross-border project in renewable energy in the EU, because in the past 5 or 10 years, even though there has been a lot of development of renewable, there's not enough cross-border project taking place. We have an instrument called the Just Transition Mechanism, which is a tool that help regions in transition or regions that have more difficulty to get into the climate neutrality agenda. Then we have Horizon Europe. I'll go a bit further in the following slide. So then we have the Innovation Fund. It's a new program that aim at funding large-scale, cutting-edge, and breakthrough technology in energy intensive industry. Started in 2020, and we just concluded first evaluation, and the first grants were signed for a value of 1 billion euro. Then we have the LIFE program. It's an older program dedicated to the protection of the environment, and then the European Maritime and Fishery and Aquaculture Fund, which aims at developing projects around coastal area. So if we could go to the next slide, please. In total, with the increasing role and increasing programs, because we'll be managing by the end of the 27 around 60 billion euro of programs. Agency will grow from 300 to 500 staff, but you could ask yourself, what's the added value of all of it? I mean, one of the added value is a bit what I'm doing today. I mean, is to support you beneficiaries, research center, university, but also companies to build projects, transnational projects. We also have a role in helping the policy feedback, which is feeding back to the Commission the results of those projects and making better programs. I'll go to next slide, please. So to go a bit more on what is of interest for you, probably is the Horizon Europe, which has been adopted last year with a budget of 95.5. So it's the key funding instrument for a green, healthy, digital and inclusive Europe. That's the different adjectives for that. It is more or less compared to the previous Horizon 2020 program. There's a lot of continuity in Horizon Europe. I mean, some of the changes are the institutionalization of the European Innovation Council. Some people might be familiar with it, which is this instrument to help SMEs to become investment and business ready, so to be able to grow. But we have also missions and a new approach to European partnership. I'll not go into details. What I'll say is that in terms of selection of projects, it will be like in Horizon 2020 through mostly competitive open call with the same criteria of excellence, impact, and the quality and efficiency of implementation. The program is divided into 3 main pillars. You can see the breakdown here in the pie. The first one, so pillar 1 is the one driving excellence, excellent science. The second one tackles societal challenge. We'll go a bit further after in the following slide. And the third one is designed to foster the innovation performance of the EU. We can go to the next slide, please. So the largest share, you probably see it, is 53 out of the 95 dedicated to Pillar 2. So this is what is called here. You have it in the middle, and addressing societal challenge and industrial competitiveness. This is where, in this pillar, the grants will be multi-beneficiary and transnational. This is probably where some of you will be applying or funding or asking for EU budget. There is no threshold per country. But what you see here is that this pillar 2 is divided into 6 cluster, and I will go in the next slide, please, to the cluster 5. So I'm trying to go little by little to the core of what will interest you, I guess. So cluster 5 is dealing with climate, energy, and mobility. This is all the activities that have the ambition to reduce our emissions or to promote renewables, or it's quite a wide, it's a broad area there. You see the budget for the whole period is 15 billion. So if you look at more or less 20% of the whole Horizon Europe, and you address the climate change adaptation, carbon capture, and energy efficiency, quite a lot of areas are there. We can go to the next slide. And then on this slide, you have the breakdown or inside the cluster 5. So go a bit deeper, and where wind will be is in destination 3, called destination 3, which is the energy supply, which, if you look at the breakdown, it represents 1/3. You can see on the slide that 1/3 of the budget for the next 2 years. So 3 billion will be around 1 billion to that destination 3. So here now we can go to the next slide. Destination 3 covers different areas. I mean, grid integration, carbon capture, and also cost-cutting, but also renewable. And the idea is, the expected impact is that we develop more efficient, clean, sustainable, secure, competitive, cost-efficient technology, like what Hiperwind is trying to achieve. There you can see that we'll have, for the next 2 years, a total of 44 topics on renewable, with a budget of 600 million. And we can go to the next slide, where it's a bit the same. This is and we can go to the last slide, because what I'd like to show is that, and if we can click on the top link, which is the draft, this one, if you can click, and this is where we will have, for the next 2 years, we'll have 4 topics on wind for a budget of around 100, something like 110 or 120 million euro. As an open, it's okay. There will be one dedicated topic on floating wind, one on okay. You can go at the beginning of the I mean, it's an easy way to look is if you put you put Control F and wind, and then you'll find the 4 topics. Because the document is 500, so you should find, so for this year, for paying for the deadline in March, we have the 2 first one, which is the wind, the aerodynamics and atmospheric flow of wind power, which is on page 178. Then we have one topic which is more on social humanities, about the social and environmental impact of wind power. And if you go below, you have one. This one on 2022 is for next year, on circularity and raw materials of wind power. But you have, I think, a third one on on wind farm control. It's also 2022. So and then to conclude, the last thing I want to say, if we can come back to the slide with the important. I mean, Hyperwind is not an isolated project. It's part of a bigger strategy from the Commission, to develop cost-efficient technology. So there's some expectation here of achievement from this project, not only from this project, but from this project in particular. And the last thing I want to say before concluding is we also constantly looking for experts. So do not hesitate to apply for experts. We will be looking for experts on wind, but not only so. And as you can do easily through the funding and tender portal, which is the third linked, and you'll find a section on work as expert. So thank you very much. Thank you, Anand. I wish a fruitful discussion for the workshop, and I'll be staying for some time to listen what is going on. Thank you very much.
Well, thanks a lot, Loic Blanchard. So that was very interesting.
And you can share the presentation. You can distribute it with no problem. Thank you.
Yes, thank you. We can have a couple of questions if from anyone right at this moment. If not, then please also feel welcome to write any questions in the chat window, and we can ask them at a later point of time. So then I will move ahead to the next presentation. So now we will introduce the Hyperwind project in more detail and go through the initial results that we have had in the last 10 months or so of this project. So I will start with the presentation here. I hope you can see the presentation and in full screen mode. So my name is Anand Natarajan. I'm from DTU Wind Energy. I'm the coordinator of this project. So this project started in December of last year. That was the formal start date of the project. But however, we started the preparation of the proposal much earlier, and this is part of the Horizon 2020. And it was answering the European Commission's call for increased of the knowledge of basic science in offshore wind energy and application of it in offshore wind energy. So to summarize, Hyperwind is addressing this call from the European Commission, where we're looking at the basic science in wind energy, coming from both the atmospheric physics as well as ocean wave models to look at air-sea coupling, and then moving to using the models to come into more and more to the wind turbine scale of looking at wind farms to the wind turbines to the components in the wind turbine in order to be able to reduce the uncertainties in the current wind farm and wind turbine design process, and thereby reduce cost of energy. So the key point is that in Hyperwind, we're trying to quantify these uncertainties and reduce the uncertainties so as to facilitate probabilistic design and do that by modeling the entire environmental chain that is used in the design process. So while we do that, we are constantly looking at the impact it has on both the levelized cost of energy as well as the value of electricity. So in terms of what the wind farm owner sees in terms of electricity pricing. So as I mentioned, we are looking at the full design chain and starting with the Met-Ocean models and then moving to the wind farm scale and looking at the dynamics of both fixed and floating offshore wind turbine structures. And not only structures, we also get into the components, for example, the drivetrain, and look at the gearbox bearings or main bearing and to determine the reliability or life within a wind farm scenario. And this is all put together in terms of quantifying the remaining life as well as preventive maintenance or predicting the degradation of wind turbine components, so that we have the ability to forecast the cost incurred in this wind farm, and also look at what uncertainties are contributing to a lower reliability or a higher cost of this wind turbine. We are also looking at the value production in terms of being able to increase the value factor by at least 1%, so that higher pricing of electricity is possible. And for at least for fixed base offshore wind turbines, we target an LCOE reduction of at least 9%, and for floating it would be much more, since we have much more uncertainties present at the for floating wind farm design, which we target to reduce. So just to put this into a more pictorial context, you see here when we get down from mesoscale models to wind farm models, we are looking at high fidelity simulations, LES, CFD simulations, in terms of being able to put together wind farm inflow fields, such as what you see pictorially represented on the left, where we capture both the wind velocities as well as the turbulence intensities and other parameters such as the shear or wear, as can be important in terms of the design of the wind farm as well as the wind turbines. And from there we go to the wind turbine scale, where we are able to look at this inflow as an input to aeroservoelastic models, and thereby see the effect on the dynamics of both fixed and floating wind turbines. And that gives us the picture for looking at life prediction of the structures of the wind turbine, as well as looking at probabilistic design of the structures of the wind turbines, as well as components such as the main bearing. So when you talk about probabilistic design, this is something that is coming up in the wind industry. In fact, the first IEC 61400 standard for probabilistic design is now being developed separately, and so this is something that is rapidly coming as a way of reducing cost for the wind industry in terms of reducing conservatism and looking at design without the need for having a lot of safety factors in it. So probabilistic design looks at being able to capture the load level in a probabilistic way, in terms of having probability distribution functions of the wind inflow and for the loads, as well as the material properties of whether it be blade stiffness or strength, or looking at bearing fatigue, or by looking at bearing damage. They can all be expressed in a probabilistic manner, so that one gets an estimate of the expected value of a quantity along with its spread or uncertainty. And a reliability model can be done, such as explained in this figure here, wherein when I look at the probability that the load would be higher than the resistance, and if this probability is no longer acceptable, then we would need to change the design so that the resistance can be higher. So this allows for a direct quantification of the impact of uncertainty, since that increases the spread of these distributions, and thereby one can determine how much of material or resistance is actually needed to go into this wind turbines. So this is also goes directly into cost, as given on this pie chart on the right hand side, which is something that we are quantifying as we move along in this project. So overall, in terms of the impact of hyperwind, we are looking at, as I mentioned, for fixed base, at least 9% reduction in the cost of energy, and we expect it would be much higher for floating. But this is translated into a lot of other benefits in terms of 2 to 3% increase in the annual energy production of a wind farm, as well as the translations of this LCOE into its other components, such as the CapEx, OpEx, and the developmental expenditure. We're also looking at the value prediction in terms of electricity pricing, and that should also increase, because we should be able to look at generating wind energy when it's most needed, and thereby allowing the wind farm owners to have a say in the price of the electricity that is being fed into the market. I think I'll stop here with this presentation, and we will go through each of these different elements, starting from the mesoscale model shortly, as well as looking at the approach taken by industry for the development of fixed and floating wind farms. So before I move on, maybe I can ask if there's any other questions at this point of time, so that I could answer them. If not, then we can move forward. Then the next presentation is from is looking at it from the industry scene, and I welcome Matteo Capaldo from EDF to take us through the wind farm design as seen by EDF, as well as looking at the uncertainties on wind farm design.
Yeah, thanks, Anand, for the introduction. Can you see my screen?
Yes.
Okay, nice. And now it's in full screen, right?
Yes, I think so. Yeah, we can see it well. Yes.
Okay. So good afternoon. This is Matteo Capaldo speaking. I am a research engineer at EDF R&D, and my activities focus on mechanics and system dynamics for wind energy. For this presentation, I will be with two colleagues, Christophe Perard, expert hydrodynamic and floating wind expert at EDF R&D, and Anaïs Lovera, that is our expert for geotechnical aspects. So this presentation is inspired by the activities we have performed, carried out with our partners in Hiperwind. But however, we would like to share ideas about a larger topic, that is all the issues implied by the wind farm development for offshore. So if you are a wind farm developer, you will deal with a high number of domains with very large disciplines. So here I reported some of them. It's a non-comprehensive list, and you can see that there are aspects like juridical or acceptability. Then you have also more technical aspects like balance of plants, export cables, wind farm layout, and this is there are also closer aspects closer to Hyperwind, like the choice of the technologies and the integration, and you will be the responsible for the integration for the subcomponents, for instance, the wind turbine on the substation. So the presentation will deal with those two latter points: the screening of technologies and the integration of subcomponents, and we will try to highlight the uncertainties that you will find on this path. So what about inputs for the technology choice? Once you have selected, you have identified a wind site, you have to characterize the wind site in terms of wind waves, currents, soils, soil characteristics, and also other parameters. So that implies that you will perform measurements on your wind farm, on your wind site, and then you need a way to translate those measurements to scatter diagrams or contours to have cases configuration to be tested. So this process is a source of uncertainties. In fact, you will see later in the presentation some details, but just to cite some of them, we can ask for how much time it is necessary to collect data to be representative of the full life of a wind farm, how many points on the wind farm surface we need to be representative. How do we translate those measurements in scatter diagrams, and what is the most appropriate return period to be selected? So most of those questions are addressed by norms, by standards that enables you, by some conservatism, to have finally something deterministic to rely on. But pay attention, because the world isn't deterministic, and all these choices imply approximations. So the quantification and the improvement of those approximation is at the core of Hyperwind activities. So finally, you arrive to, as I told you, you arrive to hundreds of thousands of configuration to be verified, deterministic configuration to be verified, and your experience, your engineering experience, can help you to exclude most of the scenario. But just one attention point is that for complex systems like floating wind, the extremes for the system can't be decorrelated to the extremes of the environment. So pay attention on that. And then usually here there is a video. I will switch on the video. I think you can see the video. Then you arrived. Then you usually model the system by using an aerohydro servoelastic model, and you look for a quantity of interest. For instance, for the floating system, there are outputs related to acceleration at the tower top at the nacelle, and then some structural outputs like fatigue at welds, movements of the platform, and so on. So I can't cite here everything, but be aware that all the tools that you are using to arrive to outputs imply some assumptions on the modeling, and this is also a term of uncertainty that is in the process. So in order to minimize all the risk, you should challenge all these points on all these choices, but this is costly, and maybe Hiperwind can help you with the meta modeling that you will see later in this webinar to explore all the parameters with a less costly process. Just to say that this video has been made by using our internal aerohydro servoelastic code called Diego. So concerning floating wind, this is just a sum up of what we have seen. Concerning floating wind, there are some points to be careful. We have seen that, for instance, coupling the substructure, the tower with the floater. When you ask for the natural frequencies of the system, you will see a shift in the natural frequencies of the tower of about 0.1.15 hertz, and this is something that very important, because whenever you do not properly couple the two subcomponents, tower and floater, you can be very wrong for fatigue. And then the second point is related to this latter. In fact, as integrator, as wind farm developer, you are responsible of the integration of the subcomponents, and this is something delicate, because normally wind turbine manufacturer, they focus on the wind turbine, as it's natural to be understood. But so the responsible of the proper coupling between the technologies is up to the developer. So this is something we take care. And the last point is concern the wind turbine forecasting and the controller. What I want to say by that is that at the moment and you are designing a wind farm, you do not have all the information of the wind turbine that will be the most appropriate in the future, because for many reasons. One is that this wind turbine doesn't exist yet, and second one is related to confidentiality. For instance, the controller is the core activity of the wind turbine manufacturer, that it will not share to you those information. So you can start by academic wind turbine, but then you have to improve it to be more realistic for the industry. Otherwise, you will, for instance, over design your structure, your wind farm. So now I leave the word to Christophe, that will explain how we have applied all that to Hiperwind. That is a specific case. Christophe, are you there?
Yes, I am. Thank you, Matteo. Okay, so now let me focus on the Hiperwind specific case, in particular on the floating configurations. So this slide is to explain what we have done based on the knowledge Matteo has described before, in order to get a base case for the Hiperwind project. So what we wanted for this project was to use a well-documented turbine that will be representative of the next step of the offshore wind industry. So we decided to work with the IEA 15 megawatt turbine as a starting point. And also we needed a floater, and so we have evaluated and selected the University of Maine floating foundation. But of course, it was necessary to make some adaptation from this open source design to Hyperwind. First, on the turbine side, because we consider that the IEA 15 megawatt was a bit conservative regarding the mass of the RNA in particular, so it was reduced. It was also necessary to redesign the tower, in particular regarding the natural frequencies Matteo has described before. So we converged to a stiff design, much heavier than the original design. And also a major difference between the open source design and the case we want to deal with in Hyperwind is the site. We are working on a European site offshore Brittany on the French coast in a 150 meter water depth. So the mooring proposed by the University of Maine, adapted for 200 meter water depth, was not applicable to our case. And so we had to make some modification on the length of the line, on the pretensions, with the idea to keep comparable natural periods for the horizontal motions and comparable offset in production and also in storm case, in order to stick to the original design philosophy of University of Maine. Regarding the floater itself, it was decided not to change the hull of the floater, but just to change the ballast in order to account for the variation of mass of the turbine and the tower and of the vertical pretension of the lines. And so the last thing to modify was the controller to be set up for floating conditions. So IFP and team work on that and set up the Rosco bottom fixed controller to floating application in order to avoid negative damping and to have a smooth behavior of the turbine on the floater. So all these modifications led to the definition of what we call the Hyperwind floating wind base case that will be used by the rest of the project for uncertainty quantification. Next slide, please, Matteo. Thanks. So now I move to uncertainties. So there are a lot of uncertainties we want to look at in the Hyperwind project, and I will just give you an overview of these uncertainties. There are two kinds of uncertainty I want to discuss today. The first one comes from the environment. You are going a bit fast, Matteo, sorry. So we have limited knowledge on the wind, on the waves, and of course on the way we are representing wind and waves, in particular regarding extreme phenomena. And there are also the other source of uncertainty to discuss is the modeling uncertainty, and so my colleague Anaïs will present later the code-to-code comparison that we have done in Hyperwind. Next slide, please. So regarding the environmental configurations, first, regarding the uncertainty, we have to mention we have, of course, limited data to characterize the wind site for wind farms, typically operating for 20 to 30 years. In general, we have limited time of measurements on limited number of locations for big farms in particular. And in addition, for floating, there is an uncertainty of the floating LiDAR regarding some wind properties like the turbulence intensity. So, of course, this brings some uncertainty in the design input, so in the outputs also. There is also the way we modelize the wind and the waves. We consider this is a stationary phenomena with normalized or idealized spectrum. So this is nice to account for the main tendencies, but of course this does not capture the full variability of the external conditions. This brings some uncertainties in the loads in particular. So of course this will have an influence on the final design. Another source of uncertainty is also the binning methods. So we consider a limited number of wind and wave directions. So also this has an influence on the load. And the last thing to mention is the statistical extrapolation method that we use to characterize extreme events that are based not only on measurements, but also on mutation models that are reanalyzed models. So they are also bringing some numerical uncertainties and also methodological uncertainties in the design. Next slide, please, Matteo. So before I leave the floor to my colleague Anaïs, I just wanted to introduce the code-to-code comparison we have done within Hiperwind. So it was a benchmark done by EDF, IFPN, and DTU on both fixed and floating cases. So you see there are some cases dedicated to align the models in the test we have looked at. And also we have looked at some critical DLCs in production, in shutdown, considering gust or storm conditions. So this is a choice of DLCs that relies on DTU, IFPN, and EDF past experience. Of course, it was not possible, to deal with the full DLC table. So we wanted to limit the number of cases to investigate, but still we wanted to consider the most critical ones. And of course, in the next stage of Hiperwind, regarding the uncertainty propagation, more DLCs will be considered. So I now leave the word to Anaïs.
Thank you, Christophe. Can you hear me well?
Yes.
Yeah, okay. So on the next slide, so I will show some results of the code-to-code comparison. So on this slide, decay test and pull-out test allowed verifying the floater dynamic. You can see the time series on the left-hand side of the time series of the surge motion during a decay test. It had been seen that the three codes are in good agreement, with a decrease of the surge motion very similar along the three time series. The results of the pull-out test are also shown. Even though we agreed on the modeling assumptions, there are some other parameters which can lead to some differences, such as the discretization of the different components in the model, and this is also a source of variability. On the next slide, the results present involve the controller. There were different controller strategies for the three codes. These differences in the control strategy explain the difference on the evolution of the electrical power, as you can see on the right-hand side. Nevertheless, the bending moment at the tower bottom is still very similar among the three codes. However, the calculation of the fatigue damage involves significant nonlinearity, and the small difference on the loads can lead to significant difference on the damage. On the next slide, it's another comparison between the three codes for the design load cases 6.1. And even though step by step, we tried to align on the modelization and all the parameters, what we model is complex, and some differences between the models occur. On the next slide, I will focus on a major difference between bottom fixed wind turbine and floating ones, is the role of the foundation and the soil in the overall response. Indeed, for bottom fixed wind turbine, the well representation of the foundation and the soil behavior is essential, as it has a significant impact on the dynamic of the turbine. In the meantime, uncertainties on the soil properties and consequently uncertainties on the foundation response can be significant depending on the level of knowledge of the soil. There are many sources of uncertainties which can explain variability in geotechnical properties. And these sources can be divided into two types, aleatory and epistemic. Aleatory uncertainty consists of natural randomness of a quantity from one point to another. And this natural spatial variability results from geological or hydrological factor. Note that the aleatory uncertainty cannot be reduced. Although epistemic uncertainty can in principle be reduced by collection of more data, by improving models, and by employing more accurate methods for measurements. It's, for instance, the methodology proposed by Hiperwind to reduce the uncertainties of the environment. On the right-hand side, you can see a variation of the pile embedded length, considering plausible variations of soil properties. So I leave the floor to Christophe.
Thank you. So this is the last slide. Just to give an example of a PhD project we had at EDF this last year to address the effect of some uncertainties in the environmental conditions on the fatigue. So the method developed was what we have called a numerical prototype. And the idea was to make a coupling between an aero-hydro-mechanical code with a Matteo model in order to avoid making beams and simplifying the spectra, for instance. So we have made this coupling and run the simulation of 20-year lifetime of the turbine. And from the model, we were able to extract the fatigue damage at different locations of the structure. And you see, for example, on the right, the damage at different locations of the tower bottom. And we found, for example, that the fatigue was approximately cut by 2 using this numerical prototype when compared to the typical binning method used in the industry. So it is a way to identify design margin, for example, but the method is quite demanding on the CPU time side because we had to run 20 years, so about 300,000 simulations to get these results. So I believe that within Hiperwind, the idea will be to deal with these environmental conditions variability in a different way, relying on meta models. And so we think that we will be able to identify the same kind of margin with maybe less demanding methodology. So that's it for our presentation, and we are open for questions, of course.
Thanks, Matteo, Christophe, and Anais. So, yeah, I think that was covered a lot of detail. So I'm sure some of you may have questions. Please feel free to ask them either openly or through the chat. If not, we will then move forward, and then you will have the opportunity to ask questions towards the end. So now I invite Mostafa Paskyabi from the University of Bergen to talk about the mesoscale and RC interaction models that we start off for the start of the design chain. Mostafa, what do you think?
Can you hear me?
Yes, we can hear you.
Can you see a screen also?
Yes.
Yeah, good. Hi, everyone. This is Mostafa Paskyabi. I'm Associate Professor at the University of Bergen and affiliated in Bergen Offshore Wind Energy. My main expertise is met ocean and noise measurements with focus on the offshore wind energy application. I have in this presentation my colleague, Hai Bui, which he is also a researcher in this project and working at the University of Bergen.
Now you're on mute, Mostafa. I think we can't hear you now.
Okay. Yeah. Thanks, Anand. Multi-scale modeling of local and non-local processes and environmental conditions for offshore wind energy applications are really key in terms of improving the performance of these offshore constructions. And there are many different kinds of environmental conditions which cause lots of uncertainty in our kind of simulations, like the local ones, just heating, cooling, and also in the area sites very close to the land, we have land land-based processes and land-sea interactions, as well as terrain and the land topography are important features that we need to account in our modeling, and they cause lots of uncertainty. We have non-local kind of processes which are important also, like the transient events, like the cold fronts or pressure systems, and also low-level jets, storms as extreme events. These environmental conditions cover a wide range of temporal and spatial scales. While over the last couple of years, many kind of different models have been used in wind energy industry, but many of them are not able to account for these diverse range of kind of scales. In this project, the main aim in this presentation, the main aim is to present the development of the multi-scale framework in the Hyperwind project, which account for as many as possible scales which are important for wind energy application. Before I start to give you insight regarding to the methodology and framework, I'm going to just highlight again why this multi-scale simulations and framework is important for offshore wind energy. Just I draw your attention to this short movie. You see here a couple of wind turbines in a wind park, and wind is blowing from southeast, and then you see the wakes and also the wake interactions and a very local kind of environmental condition. No. We have then another kind of non-local mesoscale kind of fronts, cold fronts, coming into the area, and you see the abrupt changes in the wind speed, wind direction, wakes, and turbulence intensity in the area. And the scales that these fronts belong to is this mesoscale. Therefore, you see here the farm scale, local scale are these park scale and rotor scale. But we need to understand also this kind of the mesoscale also in order to provide good insight the turbine and farm control system, and also it just influenced the other kind of important components in the turbine control and also load and other structural responses. In general, the methodology that we have already developed in this project rely mainly on the data set, observational data set we have from different kind of partners and from UIB, and also from the different reanalysis data. This is the most important part of this methodology, because we are doing lots of kind of improvement and development. We should develop this kind of verification and validation. Then we have three model components. One is the mesoscale framework model, and then microscale, which is largely simulation, and then we have surface gravity wave models, which these models have been coupled together. And the mesoscale framework, in the mesoscale model component, we will have these multi-scale kind of framework. In the microscale also the same. This is the case also in the surface gravity waves. And in this presentation, I will focus mainly on the mesoscale and surface gravity wave, and postpone the microscale while I touch a little bit, but mainly in the next presentation. In this work, we are relying mainly on two different sites, while later on we go to the South Brittany kind of sites, energy sites also. But in this presentation, I'm focusing on two sites. One is Teesside in the east coast of UK, including 27 turbines here. And we have access to the meteorological mass data set and wave buoy data, as well as SCADA data. And also Pheno1 kind of sites in here, in which University of Bergen in between 2015 and 2016 have deployed lots of kind of instrumentation like sonic anemometer very close to the sea surface to measure turbulence, wave, wind interaction in 15 meter, 20 meter high frequency, and also different LiDAR kind of configuration to measure vertically, and also to measure wake in the Alpha Ventus, which is the wind farm containing 12 turbines in the vicinity of Pheno1. We have also access to SCADA data, but from the RAVE project. In this presentation, while we have done lots of kind of verification and validation versus the SCADA data. I'm not going to show the SCADA data here, but all results have been verified. And we are using also satellite measurements and other kind of reanalysis data sets. As I mentioned, we are working on the multi-scale kind of framework, and we need to know the scales and then how to separate the scales and then how to make a framework to couple different model together to just could capture those scales. And for that reason, as I mentioned, we use here we use mesoscale model. In this study, we use weather research and forecasting model, which hereafter I use just in short WRF. And in our mesoscale WRF model, we have 3 domains here: 9 kilometer, 3 kilometer, 1 kilometer, so that we could capture different scales in the meso to the farm scale. And also we have another large eddy simulation, which is our micro scale. Still, this also under the WRF kind of model domain, which is called WRF eddies, so that we can go down a scale towards the 200 meter and 40 meter to capture the turbine and rotor scale also here. Therefore, we have 2 different kind of domains: micro scale domains and also mesoscale domains. And in the WRF model, we need to set up kind of the model to capture the vertical kind of variability. Here we use different 60 kind of levels in vertical. Try to just focus mainly within the first 200 meter to capture all variability relevant for the offshore wind energy. And other important thing is that our mesoscale model relying intensively to lots of parameterization. We have lots of tunable parameters, which are the resource of uncertainty in our model. Model by itself, due to the solvers and other kind of technical implementation of algorithms, has also its own error. Therefore, error quantification and uncertainty quantification is one important part of this study. And just shed light on one of these kind of uncertainty resources, which is the different parameterization. We have classified parameterization involved in 3 kind of groups. The microphysics parameterization, radiation, and boundary layer. You see a bunch of kind of items at each of these classes, at each of this group. Just I ask you to remember these 2 kind of configuration control, which use a certain kind of parameterization at each of this group, and the best, which is parameterization that works fine with the mean kind of quantities. The complexity here is that we should develop lots of experiments to understand which kind of parameterization is good for our study site. And the other important question is that whether this parameterization can be used, whether these parameterization are site dependent, if we move from T site to Pheno1, whether we can use the same parameterization, or we should also think of other kind of near optimum parameterization for the new site. These are the questions that we need also to answer here. We have worked out on a wide range of kind of processes. The varying atmospheric stability conditions, several diurnal cycles that we have lots of variability in the solar radiation and also the heat flux and cooling and heating, and also wind wave interaction. And we took also look on the wind ramp, low-level jet, and also the open cellular convection. We have developed kind of the detection algorithm for each of these transient extreme events and in general atmospheric events. But in this presentation, we decided to focus on open cellular convection, in which is really important, and it's really challenging because our models and the different configuration behave really bad in during this process. And therefore, this is really challenging for us to provide as good as possible parameterization to resolve the kind of fluctuations, and also to capture the phenomena in a proper way. Okay, open cellular convection in general is the 3-dimension convective atmospheric circulation. And these phenomena occur whenever we have cold air top of the warmer ocean. In this figure, you see, as I'm showing by mouse, here you see the sea surface temperature in red color, and in green you see the temperature at 2 meter height. And you see here in this time, we are getting colder air top of the warmer ocean. And here we have unstable condition, and it means that the favorable conditions for formation of these convective plumes and convective cells. And you see here in many kind of places we get these kind of convection, these cells also, the convection. And we can also take a look on these convective, large scale convective events from the satellite images. In this image, you see the from the satellite, you see these cells, convective cells, as I'm showing here. You see these circular kind of elements of clouds. This is the image from satellite of cloud cover, and we see the trace of footprint of this convective cell in the cloud cover. Okay, as you see here, we have kind of the circular kind of pattern here. Alongside the edge, we see clouds and very strong vertical velocity, but in the center of these cells, we see somewhat clear sky with very strong downward kind of vertical velocity. This kind of, and you see here in both in T side and Pheno1, we are getting the same process. And therefore, we can just answer the question whether our configuration works for both sides finely or not. We need to develop a kind of site-dependent configuration. Okay, the spatial scale of these cells is between few kilometers to 100 kilometers. Therefore, by accounting the advection velocity, we see that they cover minute to hour scales, and they cause lots of fluctuations, and then fluctuation and variation in the power within this kind of window. And in the next presentation, I just try to investigate whether they can influence also turbulence, smaller scale. Okay, here, just to give you insight about the model behavior here, you see here convective cells. As I mentioned, around the edge, we have clouds and we have vertical, positive vertical upward motions. And in the center, you see the negative because it's downward. And you know, T side is really interesting because this is the seaborne kind of creature. And when it reaches to the land, it just disappears. And here we have very complex interaction between this process and land also. And here you see the zoom in of these kind of cells in this area. You see, again, these cells are really active in the southern North Sea. And we are getting here in these the T-side environment, very complex interactions between these cells and also the wind parts. As I mentioned, then we get lots of fluctuations in the generated power. And here we are going to see how our model and different configurations react to the model resolution, which is the most important kind of factor that we need to check. We selected 2 days of active convective cell events. 21st of November, between 21st of November and 23rd of November. And convective cells happen here, very strong oscillations, and this plot is mean, and the next plot I will show the oscillations also. In the 9-kilometer resolution, we have done different kind of set of experiments. For example, here we change boundary layer, kind of parameterization, and we develop different kind of experiments. And you see here, the vast majority of these experiments cannot get either this low wind before, prior to the fluctuations, or also the fluctuation properly. Just one of these models, which our optimum kind of optimal combination of different kind of different parameterization works well, even for 9 kilometers. But in 1 kilometer, the case naturally is better because we are capturing more scales, but still it's not really a reliable kind of parameterization and also agreement between observation and also the fluctuations in the OCC event. And here, in short, I just to make less messy kind of plots of different experiments, you see here the control run and best that earlier I asked you to remember. In control run, you see that in 9 kilometers, we cannot capture, and this is our oscillations caused by this OCC event, open cellular event. And you see here, not in these low wind before the oscillations, and even in the oscillation time, it cannot do anything. But our best configuration, at least in mean sense, it can just capture the physics, even in the variation, even in 9 kilometers. But naturally, 9 kilometers, we cannot capture these kind of small scale fluctuations, which has between the minutes and the variation between minutes to hour. And if we move to 1 kilometer, we see here the control run is behaving better, but our best run is providing more kind of fluctuations here. And then the optimal combination, which we combine everything together, can show more fluctuations. But still, we need to do verification and validation of this. And we have put everything in the Taylor diagram to see more kind of statistical kind of assessments of different parameterization. And here you see we provided 3 sets of parameterization, which we have changed the microphysics, you see by MP at beginning, and then boundary layer, and then radiation. And you see here our optimal combination is behaving well in all of them. But still, in this plot, we need to understand, okay, which of these, we can see here that this optimal combination is doing better in capturing both oscillations and also in the low wind prior to the oscillations. But we are going to explore this in a more kind of clear way. And here we have provided these kind of bar plots. We have different kind of experiments in horizontal axis. You see different experiments we have developed, control run, best here, and other kind of changes in configuration. In vertical line, you see a standard deviation. We pick up the duration of the strong fluctuations in the during OCC event, which is our transient event, and then estimated a standard deviation of observation here. It's shown by dashed line here. That's our reference, and we would like to see whether which of these models, model configuration, can reach to this standard deviation, and which says about the variation. And we see here our best model is not behaving well here. It's far away from this standard deviation. And you see other kind of models like this radiation configuration, they are doing better here. And we are getting here our estimation also for this guy. Then the whole thing has been done so far in the T side. Then I come back to my questions. If we do this configuration we have the same kind of process acting both in T side and PHENO1, whether we get the same kind of distribution of the standard deviation for the PHENO1. For that reason, we have done the same kind of experiments and analysis. And the same thing for 2 domains. Here in the orange, you see that I provided a 3 kilometer kind of standard deviation. In blue, the 9 kilometer standard deviation of models, each model. Then in PHENO1, the same thing. Orange is the 3 kilometer model standard deviation. You see that if we just focus on 3 kilometer here, in PHENO1, we see that this guy, which was this the BL4, is not behaving like the other model. And this analysis, alongside with other analysis we have done, suggests that we need to be careful about the site, because the site vicinity to the land and also the kind of regional processes specific for the specific site can determine the optimal or near optimum kind of configuration. And also we have done, as I mentioned, I don't want to touch more LES. We have done WRF LES also here. You see here our observation and also our optimum kind of configuration. The results of WRF mesoscale model. And green and blue, on green and red, you see also large simulations for a short period just to check this scale. I will come back to this in my next presentation. Okay, with this, I have shown very briefly about these mesoscale and microscale. There are many things here that I couldn't provide here in terms of the reducing uncertainty using data assimilation, those things, but I just leave this mesoscale modeling here and start very brief explain about wind wave interaction. We are using here the coupled system, WRF-SWAN called a coast model. And here you see that whenever, if we have a wave, regular wave, just propagating over under the wind, when wind and wave are aligned, they are propagating at the same direction. You see that the wave-wind interaction can just influence as 40 meter, for example, in very kind of idealized kind of scenarios with large eddy simulation. But when they are opposed to each other, you see that this kind of interaction can just modulate the overlying atmosphere and wind on up to 100 meter height. Okay, therefore it shows the importance of wind-wave interaction and also wind-wave misalignments in our multi-scale framework. As I mentioned, we are using the wave model. In this case, we are using Swan wave model. And another, this is WRF, and then we coupling WRF with another model. And WRF passed the wind speed, and then Swan passed roughness length. But the problem here is that we are using different model, and whether the coupling is functioning well, whether we are conserving all conservation of mass, momentum, and energy exchange between these two models, this uncertainty is letting us to work out on another module that we need to use in the wave model, so that to maintain the conservation of momentum and energy and mass between these two different models. And here, just my last slide, we have made a very simple run of the wave model in sometime in July 2015 for a few days to just compare between the model results with wave boundary layer module and without wave boundary layer module. And we are just take a look on the significant wave height, wave period, and wave direction. And observed significant wave height shown in green, and the blue is the wave simulation with wave boundary layer model, and orange shows the simulation without wave boundary layer. And you see here, in general, they are in agreement, but whenever we have a strong wind and wave events, then you see that the wave boundary layer is doing very good job. It suggests that in the transient events and extreme events, these wave boundary layer module can play very significant role in making these interactions work just correctly. And also these wave boundary layer in here in blue, you see that it's capturing the wave period also way better than this the without wave boundary layer, and this is the case also for wave direction. With this, I thank you, and I would be happy if there is any question. Yeah.
I don't see anything in the chat window, but please feel free to ask if they have any questions. Otherwise, in the interest of time, we will move forward. I think the next presentation is also from you, Mostafa.
Yeah, I'm just sharing this. Okay. Here we are going to discuss about in the previous presentation, the main focus was the flow field in the absence of any wind turbine. We just focus on the multi-scale modeling. But in this presentation, the main aim is to see how flow field also react to the presence of the wind turbines and how our multi-scale modeling looks like here and behave here. And as I mentioned you, the main focus for the previous presentation was the mesoscale multi-scale framework, but here we are focusing on the same multi-scale, but this time for the micro-scale modeling component of our framework. And yeah, here we are using large eddy simulation to close this loop. There are many kind of engineering wake models, or the model can be used for this purpose, but they are very robust, very fast. They provide lots of insight, useful insight, but they provide very limited information about the flow field. However, large eddy simulation also is really computationally expensive, but it can capture turbulence, wake evolution, and wake interaction. Lots of insightful information that later on can be used to develop reduced order model, surrogate model. In that sense, it's really, really helpful tool. In this presentation, the main focus is towards two different LES models. One is the WRF LES model, which is the built-in LES in the WRF. And I mentioned that we use here two domains for this WRF LES. And then the other is using another independent, a different LES, which is called parallelized large eddy simulation model, in short PALM. And this, for this, I decided to divide this presentation of another LES in two parts. One is take a look on the non-mesoscale nesting PALM. PALM act as a standalone model so that we just reproduce the observation and compare with the observation using precursor run. We don't nest with the mesoscale model. The next one will be offline WRF PALM. And just regarding to the WRF LES, as I mentioned, just remind, we are using for the mesoscale configuration 3 domains, 9 kilometer, 3 kilometer, and 1 kilometer. And then for the WRF LES, here you see the tiny around the T side. The focus in these WRF LES is T side, and this is the smaller domain, 40 meter in T side. But the interesting kind of question here is, we are talking about multi-scale kind of modeling. And I have just separated these two into two model framework, one mesoscale and other microscale. But the question is whether mesoscale model is able to capture any kind of turbulence in our area of interest. And I'm going to answer this question by taking a look on the turbulence intensity and then see how WRF LES also react to these questions and this concern. And like the previous presentation, we conduct a series of configuration in the WRF. You see here 5 different configuration in WRF mesoscale model with 3 kind of domain at 50 meter height. We just focus on the OCC event, open cellular convection, the same event that I explained in previous slide presentation. And then over this time, which we have the OCC oscillations and fluctuations, we calculate turbulence intensity from different model configurations here as shown here. And we have the turbulence intensity calculated from meteorological mast. And you see here in this period, we have turbulence intensity around 10%, but our WRF mesoscale model is not, even in the multi-scale form, is not able at all to capture any turbulence intensity as expected. Now we move towards the 200 meter and 40 meter. And we see here, if we compare with the observational data, which is here, we see all configuration of these microscale simulation can capture these turbulence intensities somewhat. And this is really the difference. And that's really one improvement that these kind of simulations is doing by accounting for the smaller scale kind of features. Now, just I take a look on the power production. This time I take a look on the mesoscale kind of setting here, the 3 domain kind of setting here, but this time put the wind turbines in our simulation in 1 kilometer simulation, for example, and all of these kind of domain simulations. And I focus on this turbine, name it turbine 1 and turbine 27. Okay, and as I mentioned you earlier, we have done verification and validation versus the SCADA data, but here I'm just not using any SCADA data, but it has been verified already, these plots versus SCADA data. Okay, we are here in this slide. Take a look on the wind speed and the turbine power output. Therefore, the top panels show wind speed, and the bottom panels show the turbine power. I'm talking about turbine 1 and turbine 27. Okay, in 9 kilometer simulation in control run, you know, the distance between T1 and T27 is about 4 kilometer to 5 kilometer. But while these, the course domain is 9 kilometer, and then there is no differences here between wind speed here and here, because this is subgrid scale and model is not able to capture this scale. Therefore, these are just coincide to each other. There is no difference. They are the same. And also, this is the case also to the power output, because we set these turbines using the kind of information of these the power curve and other information. We set up these turbines in our mesoscale simulations, and you see the power output for turbine 1 and turbine 27 are also the same. Okay, therefore, because of the resolution. Now we move towards 1 kilometer resolution. Since the distance between these two guys is about 4 to 5 kilometers, and the resolution that we have now is about 1 kilometer, then we can capture some kind of turbine farm-induced kind of modification of flow field. And this causing the discrepancies between these two turbines. It's natural if we use the LES model here, we are getting kind of more kind of distinctive kind of discrepancies, because we can capture more vague interaction for the power output. And I should mention that here this is a control run, and we have here the best configuration that already I mentioned a couple of times. And comparing with the best configuration with the power output, we notice that the power output for the best configuration is really promising. It's really in good agreement with observation from the SCADA data, and it's really reliable. And as I mentioned, this is really reliable, but in mean sense. While it can capture here the fluctuations, but more kind of fluctuations with the time scale, which is less than minutes or a minute, around a minute to half an hour, it's not able to capture those kind of fluctuations properly. Okay, with this, I move towards the second kind of the micro scale modeling system that we have used in this project. This we are using PALM model. As I mentioned, I explained PALM as a standalone compared with observational data. You know, I'm not going to develop the idealized kind of large eddy simulation. It's realistic, but this time using the no mesoscale coupling with the LES model. Here, the main study area is the FINO1 and also Alpha Ventus, including 12 turbines. And yeah, the start point here for constructing real kind of PALM standalone simulation is the turbulence intensity. We take a look for the 3 months on the turbulence intensity diagram here as a function of the wind speed, and this is the well kind of known kind of pattern here. We see here, I color coded this with the atmospheric stability kind of parameter here. Negative values stand for unstable or convective kind of environment, and positive values stand for the stable. And you see here in the wind speed between 5 to 10, we have a stable condition, while in the low wind below 5, we have very strong kind of convective kind of atmospheric boundary layer with turbulence intensity up to 40% also. And I'm going to just to show you the how we did this simulation with PALM standalone. First of all, we started this area and then the target turbulence intensity. Then, since we know that this is a stable, over the study period that we select, we pick up all kind of snapshots with the same kind of turbulence intensity under stable conditions, and then obtain the average value. And then we initialized model based on the average observational data set from the site. And here I put just 2 turbines in raw here, in line here, and the wind is blowing from this left to right. And this is YZ kind of plane here. And you see here we are talking about the stable boundary layer, and there is an overlapping between boundary layer, top of boundary layer, and also the turbine rotor plane here. And it has lots of implication in terms of load. And now, after doing this kind of simulations, we get the data from the turbine side to calculate with the SCADA data, and also from FINO1, which I have shown here. And then do comparison with versus FINO1 kind of data and also pollen results. Here you see if we compare the wind profile during these conditions, which turbulence intensity is around 10%, we get very good match in the wind profile by palm. And we have done different palm configuration with different kind of resolutions. Here you see, for example, red line in 80 meter and then 40 meter in blue line, blue color here. And turbulence intensity at the surface also is about 10%, and then it's gradually reduced. And turbulence intensity at different height calculated from sonic anemometer are in good match with our palm standalone simulation. But the problem here is that this is really time consuming because we need to do lots of try and error to find out the optimum configuration, and it's really time consuming. In terms of computation, cost also is really not cost effective. And the other thing is that our main transient event, an event that we are studying, is the OCC, which is convective event. And if we select this area, we get into real trouble in terms of computation because it will not converge easily. It's really hard to find the proper kind of configuration setup. In general, when we are working in the convective kind of scenarios, I recommend using this kind of offline nesting. It makes life easier, and it's become more kind of efficient way to do that. And here I'm going to just explain that towards the end of my presentation, this offline nesting. But before just explain this, I'm going to raise a question. I talk about the OCC event, transient event, and mentioned that these oscillations are between minutes to hour. And the question is whether these oscillations can influence a smaller scale, which are relevant for structural responses and pitch control and other kind of important applications. And to answer these questions, we have done a very kind of tentative test just to show you how it looks like. But just I explain this and then come back to this question. We have done already the 3-domain WRF simulations, and we pick up the 1 kilometer, which is a finest kind of WRF domain, and then develop a coupler. Coupler here do all interpolation, horizontal, vertical, along the pollen boundary edges here. And then we do also extra kind of efforts to make sure all conservation of momentum, energy, and mass are in place, because we should not generate any artifacts along this boundary, because we can easily generate lots of gravity waves which with different phases speed, they propagate into the domain and they influence flow fields significantly. Okay, then after developing this coupler, we start our palm in the offline mode nested with this 1 kilometer WRF. And here I have used then the time series around 1 wind turbine to generate the input for structural analysis code. I used here in this simulation the TurbSim for different events, and then pass the results to the FAST, and then take a look on different structural responses to see whether the OCC event versus non-OCC events can make any distinction, whether they can do anything in the smaller scale. Okay, to explore this, I just we did a very simple kind of experiment here. We take a look here, just observational data from our sonic anemometer at 40 meter and 20, 40, and 80 meter heights. Okay, this is in top panel, you see the stability parameter. And as I mentioned, negative values mean unstable and convective, and positive are stable. And we selected 2 episodes here. One OCC episodes, which we have our OCC, open cellular cell, which we know that it's unstable, it's convective, it should be negative. We select another episode, which is also convective with close value to this. And this is somewhat close and as non-OCC. But the other kind of criteria that we need to fulfill is that we need to have the same inflow field for the non-OCC event like the OCC to just could compare them together. And by the inflow, I mean the same wind speed and wind direction. And I should mention that it's really hard to find these non-OCC events, because if we have the favorable conditions for OCC that occur, and then it's really hard to detect another non-OCC the same characteristics of OCC. But we are lucky here to find some episodes which are quite the same. But we couldn't find any kind of snapshots here with the very close wind direction. Okay. Therefore, in these two episodes, we extract the sonic high frequency data set and then do a spectral analysis to see whether we have any changes in energy content. We see that we have elevation of energy from the energy containing subrange towards the inertial subrange, towards then the dissipation subrange. Okay. After this, we select this same kind of time series, about 30 minutes of high frequency time series from different sonics at different height, and then pass them to our TurbSim to generate input for the NREL fast model. And therefore two kind of different events, OCC, non-OCC events. Here I'm not going to interpret the results, but the main message is that whether these OCC events can make any distinction for a smaller scale and for the structural kind of responses, and see in the spectral domain, comparing between rotor kind of torque and also generator torque, for OCC and non-OCC, we see kind of effects of the OCC events also in modification, the frequency modulation of these spectra by elevation of the energy at different kind of frequencies. Okay, therefore, the answer is that it might cause modification in the smaller scale, but we need more kind of investigation to verify and this point, because that's something that we recently has started. Okay, now I'm just moving toward the last part of my presentation, which is about the offline nesting. This is the first time we are doing under umbrella of this project, because we have started last year this coupling, and we could just finish it and could start to just do some verification. The first important step here was whether our LES can represent these kind of OCC events. And here, for that purpose, we just conducted a 357 meter resolution kind of palm simulation for about 512 grid points along each axis X and Y to cover Pheno1 platforms. And you see here, we have done a very tentative verification, and by comparing this with the Pheno1 measured wind speed, we see that, okay, we are capturing these phenomena properly in our LES model, which nested offline with WRF. Okay, this is the first step, because that's important. As I mentioned, if we don't do good job here in terms of coupling, we get lots of gravity waves propagating from different boundaries towards the inner domain, and which mess up everything. Okay, now afterward, we need to put wind turbines, and then we are using then another WRF simulation, final resolution, putting turbines, alpha ventus turbines in the vicinity of these Pheno1 platform to see wake characteristics. And also we have then output of the power and many other things that, for the sake of brevity, I didn't put here in this presentation, but just show you the results, the recent results that we got in the WRF Palm kind of coupled system. And you see here the wake evolution from our system here, which has been nested with a mesoscale model. And you have seen in the previous slide, we can then bridge easily these towards the structural analysis and structural responses. And I have done very tentative, just visual and quantitative comparison versus our LiDAR measurements, but not at the same time, but just to see whether these wakes are resemble to what we can see in our LiDAR. I would say that this is quite good results in terms of wake shape and wake interactions. And you see here the complexity of these events also. Wake is changing a lot, and that's really induced lots of kind of work to the control system to make efficient the efficient yawing towards the dominant wind, and also the other kind of technical things. With this, I finish my presentation. Thanks for your attention.
Thanks a lot, Mostafa. That was very detailed and very interesting. I think for want of time, I think we'll proceed further and then we'll come back to a discussion about all the results. So I now invite my colleague Nicolay Dimitrov to continue with on the surrogate models approach.
Yes, thank you, Anand. So yeah, let me just share my screen and yeah, I hope you see my presentation screen. So now we will talk more about surrogate models. So and how we can use them in uncertainty quantification, and more specifically, first, I mean, we would need to do some power and loads prediction in order to do the uncertainty quantification. So I think this work is a little bit more in progress. Sorry, can I ask? I think there's someone with an open microphone that makes. Yep, thanks. So yeah, so. This one is a little bit more work in progress, I think, compared to some of the other presentations you saw. So it's a combination of what we've done already and what we intend to do. So first, maybe discuss why do we need surrogate models. I hope we all agree that we need them. And there's a couple of scenarios that we think about. And the first is maybe, what if we do not really have a physical numerical model to model or to map some measurements, and instead then we would need to resort to this type of regression or classification type of data-driven models. So this is one potential use of the surrogate models. And the other one, which is maybe even broader, is what if we simply have numerical models that may be very complex or time-consuming to run for very large studies. So instead, maybe we run them for like a selected set of cases and then map their behavior, and then use the surrogate models then to run some more time-consuming or more number of samples, like in the problems of like uncertainty propagation, optimization, or some integration over range of inputs that could be, for example, over a fatigue load lifetime assessment, and integration over environmental conditions, or reliability analysis. Then we have thought of several specific scenarios that we are investigating in Hiperwind. And the first one is for the wind farm effects. So imagine we have a wind farm, and typically we would like to, to know the loads and the power outputs at every turbine. But because of the wakes, we have variations, and then disturbances from the surrounding turbines. And because for each wind farm we have unique geometry, then these disturbances may be different. And because we have many turbines, then if we want to describe these disturbances for each of them individually, then it would require quite many variables, and it would also be it will need to be repeated for every new wind farm you're investigating. And at the same time, so if you want to run a surrogate model, you need to have many variables. And in order to somehow alleviate this problem and to make the possibility to have surrogate models that are more generalizable, we would need to parameterize these wake-induced effects, or at least parameterize the wind farm layout, so that we know how to include the layout effects on the wakes. So this is one let's say task that we're working on, and the other is load time series, where if we go for higher frequency, so instead of looking at maybe the classical 10-minute statistics that very often are considered for surrogate modeling, then what if we look at the actual higher frequency time series? That could be useful, for example, for simulating transient load cases. Again, if you have to use aeroelastic load simulations, it could be also time consuming to do many simulations, and instead maybe one could do a more computationally efficient approach by using surrogates. Or other possibility why we would look at such models could be, what if we have a proprietary or a confidential model that someone doesn't want to share the full wind turbine design properties, but instead maybe it could be possible to share a surrogate model which has very similar behavior, but on the other hand, it doesn't reveal all the design details. So that could be another kind of a scenario where such a model could be useful. And the third could be like, what if we have a model that maybe is maybe is numerical, but we have maybe parameters that's not easy to measure or not easy to update with data. So maybe a more flexible approach could be instead to train a surrogate model where we have some parameters that are more easily updatable by using measured data than using some Bayesian approaches or transfer learning, for example. Then the third general scenario is related to what I earlier mentioned, integrating quantities over some long-term distribution. So in this case, is the lifetime fatigue that you can integrate and say and look at how to use this for lifetime assessment and for reliability analysis. And then there is two problems here. One is the integration in itself. So how many samples do you need to run in order to obtain a proper let's say estimate of the integral that could have that could depend both on the sampling, how the strategy, how you place your samples, and then also, of course, if you use the surrogate model instead of the more advanced model, it could also save time. So we are looking at all these things in the project, and maybe I will go in somewhat more details in each of these cases now. So for the wind farm, and here this is work by us and by our partners at IFPEN. Yeah, we are, as I said, we're trying to find out how to go from the external conditions and the wind farm layout. So this is as our inputs, how to predict mean power output and loads. If we look at the mean power output, maybe it's a very simple approach is to just use the quasi-static wake models. So then you input the mean ambient wind and input the turbine positions, and then you run through the model and you obtain the mean power outputs. So this is very good, very efficient. I think in most cases it's even at least as efficient as the typical surrogate models, because these quasi-static models are based on very simple functions. But it would normally only give you power and local wind estimates. So if we want loads, then we go to the dynamic load simulations that require significantly more computation efforts, because there you go from this ambient wind, and then on top of the ambient wind you superimpose some turbulence which also should include the wake effects. So there's two ways to do it. You can either do it dynamically, so that the wake is as a separate addition to the turbulence time series, but also you can maybe also add it as a local wind, so superimposed to the mean wind field, and then superimpose the turbulence fluctuations. But altogether, the idea is that you have this turbulence time series, then you do load simulations, which is in the time domain, also takes lots of time. Then how to, in order to be able to shorten that, we would like to have a surrogate model that uses input as the turbine positions and properties in the ambient wind. So only a very simple inputs, and then provides directly the mean load output or the mean power output. Yeah, what are the challenges in this? First, we can only use, we need only to have a limited number of inputs. So we don't want to have, for each wind farm, to have 100 features or something like that. And we also don't want, it's not desirable to have the need to train a new surrogate model for each wind farm. So it has to be somehow generalizable. So with this in mind, we want to parameterize these wake-induced effects in only a few variables. So yeah, this is the question. So that we're trying to look at. What are the variables that really, these parameterizations that result in the smallest error? And also then once we find out, so we would also, in order to also supply information to the other tasks in the project, we would like to, of course, study the uncertainty in this type of parameterizations. So this is an example of this approach. One of the approaches that we are testing in this one is based on an autoencoder and some layout derived features. So the features that we use is just relatively to the turbine in question. You consider each other turbine, you describe it in terms of distance and relative angle between the wind speed and the turbine. So this is like 2 features per turbine. And then, of course, this would mean many features. And in order to reduce this number, then we pass this through an autoencoder or the encoder part of an autoencoder model using neural networks, which reduces reduces this variable space to a few latent variables, maybe in the order of 3 to 5 seems to be sufficient. And then you feed this as an input to actual loads and power surrogate together with environmental conditions, and you do get load and power estimates. So just to show you how it works and how it looks, this is an example of this is a wind farm in the North Europe, offshore wind farm in North Europe, and this is a turbine in the middle of the wind farm, and you can see the power production at 3 different wind speeds as function of wind direction. And of course, you can see the comparison between the power output from the pi wake, so the actual quasi-static wake model, and a surrogate model that's trained on this one. I think that's fairly good result. Of course, this is something still under improvement and studying. And we are also developing, just to let you know, a Python package that should include this type of functionalities, and it's called HyperSim. So please, I hope that in some months you will be able to use such tools by yourself. Then let's go on to the loads time series simulation. That's the second case. In this one here, the main contribution is by our partners from ETH. Again, maybe just why would we need such a tool? This is just a breakdown of how really a typical aeroelastic tool looks like. So we need some turbulence generator, which provides some high dimensionality turbulence field. Then you go through the blade element momentum method to find out the aerodynamics loads, and then you have a controller that basically controls the pitch angle and so the way the turbine behaves, and then you have, of course, the structural response in the generator. So all these parts, again, they are quite some of them could be computationally expensive to run, but some of them also may be confidential. So how would we want to replace this? First, maybe if you want to run computation efficient simulations, and this makes sense, of course, only for transients, because then you consider the time series rather than the 10-minute statistics. The other thing is, as I mentioned, if there's a confidential part, maybe then maybe you can just share the surrogate model instead of the full model. And then basically, again, the model updating, that could be another possibility. In order to facilitate that, we could make a surrogate model that goes directly from the turbulence field, this high dimensional input, directly providing time series of loads and power. And so this is just a summary of how this should look like, as I mentioned. So you have this high dimensional input field, which is like maybe a movie, so maybe many frames. So it's a 3D input that is discretized in space and time, and then you need to provide time series output, which is contemporaneous or with the inputs. So then, of course, it shows this low time series. Of course, you can look at peak values and accumulated fatigue if you just sum the time series, and then it should hopefully have a similar behavior to the aeroelastic model that you want. You want to train this based on some aeroelastic simulations as a source of information. So what is the type of model that you need to use? It's an autoregressive model, because it needs to first predict some of the time series based on the previous values, and also it needs to have the exogenous input. So it means that in order to have this autocorrelation in the signal, which is the time, how to say, the inertia into the loads and the rest of the system, then you need some autoregressive component. But in order to take the external inputs like turbulence, then you also need these exogenous inputs. So this is what how you should put it together. And in order to also these exogenous inputs not to be overwhelmingly many, then what you do is you take the turbulence box and you do a dimensionality reduction, for example, by principal component analysis. So that's basically how we've tried a few examples of this, and this is just a summary of one particular time series. So you get this high dimensional input in space and time. You run it through the dimensionality reduction. You use a few principal components to provide this turbulence input, just the most relevant part of the turbulence input. You add together with the history of the vibrations and the turbine operating characteristics, and then you predict the future time steps, and then it runs as autoregressively. And then this is, as you see on the right hand side, you can see the comparison between the actual simulation that's used for the actual load simulation, and then the time series, and then the predicted time series using this surrogate model. So yeah, this is I hope that we of course need to test it further and expand to make sure that it is valid in all situations, but I think it looks very promising. Then just something which is still, this is, as I said, this is something that will come in the coming months. It's some more efficient lifetime fatigue damage estimation based on improving the way that we do this integration over the joint distribution of environmental conditions. So this is main contribution by the other partners at EDF. And yes, so what do we have? We have these input conditions that they have, as I mentioned several times, they have joint distribution. You need to somehow sample this joint distribution. And then for every of these sample points, you need to run some simulations. And then based on that, you do a probability weighted integration to get to the final result, this lifetime equivalent loads, for example. And the fact that we need to do sampling means that if we work on regular grids, then we are subject to this curse of dimensionality. So if we have many inputs, then then the number of required samples grows exponentially. And then the other issue is that we also, if we want to go for uncertainty propagation, so not only find one specific value for the lifetime, we want to find its uncertainty. Then it means that we need an order of magnitude more calls to the function. So how do we tackle this? It's two parts. So first, we try to improve the sampling by trying to find things like this adaptive kriging, and then or this quasi Monte Carlo sampling, and then and together with that, we also try to find how to do the integration in a better sense by this, as you see, this quadrature methods. So and all together, hopefully, this will make sure that you get an accurate integration with fewer sampling points. And then an additional, how to say, a way of improving this is, of course, that instead of also running all the samples on the high fidelity simulation models, then maybe one can first try to run some simulations on the high fidelity model, again, by using this smart sampling, and then train a surrogate model that could be used for more extensive sampling. And I think that's all for my presentation. And if anyone has questions, please, you're welcome to ask now.
Thanks, Nicolay. So you can have a couple of questions to this presentation, or you can see that in the chat window we have some questions, but that's for the earlier presentation, I think. So
I actually have a question for this one, please.
Yes.
When you are doing your surrogate model, are you able to quantify the uncertainty of your model?
Well, in the end, yes. It's just depends on the model. Maybe it may be different approaches. For example, if it's a Gaussian model, then typically you have the uncertainty as one of the outputs. Otherwise, for example, if it's a neural network, and as in some of the cases for the wake simulations, then you probably need to run an ensemble model or some kind, some kind of maybe some kind of, again, an uncertainty propagation or bootstrapping in order to estimate the uncertainty or cross-validate. So the typical cross-validation approaches. But maybe, of course, if there's I don't know, maybe Stefano could also say if you have any comments on specifically on the models you're using, for example.
Yeah, I agree, actually, Nicolay, with both the techniques you mentioned. Indeed, also for the methods we use, bootstrapping, or if you use Gaussian processes, can also give an estimate. However, remember that we are surrogating one specific model. And one of the things that has been figured out by our colleagues and has been presented earlier is that, well, what is the most likely source of model error is actually the discrepancy between different simulators. And Surrogate one simulator. So I would say that both the aspects have to be taken into account. And as far as I could see from the report, probably different simulators have a bigger difference in performance than Surrogate with respect to each simulator. Just a side note, and this is something we cannot handle because I mean, ensemble modeling, indeed, Nicolay, I think is the most common use technique, like Bayesian model averaging and so on, kind of error informed. I hope that goes in the right direction.
Thanks.
Thanks, Steph.
Okay, so if there's if you don't have further questions for this specific presentation from Nicolay, we can open up for all the presentations. So I see a question here on the chat, which is I think directed to the mesoscale modeling that was presented by Mostafa. So maybe Mostafa, you can explain about it also orally that. I was talking about how the wave models work, and does it generate surface roughness, or is it also estimating the wind flux at the surface layer? Maybe one by one. I think there are 3 questions here.
Yeah, thanks for raising these questions. Actually, we in my presentation here, I just showed it's the Worf-Swan coupled system in which the Worf model just estimate the roughness from wave inputs of significant wave height, peak period, and also wave direction. However, we have done already, I haven't shown here, the misalignments between wind and wave, because it just has lots of strong implication on the power generation. And this has been implemented already in this Worf model. On top of that, we have done another kind of offline kind of nesting, which is under a process of validation. Therefore, we noticed that we can do offline also these, instead of having coupled system in offline Worf and wave, so that get the same kind of somewhat reliable kind of results. Therefore, many different things in this wave-wind interaction is running in this project. And regarding to the wave and your question on the how we account for the wave and wind, yeah, this is something that intensively we are working on that. One of my PhD also is working on that, on the PAL model by itself. In this way, what we have done already, developing a simple kind of wave boundary layer model. Not only we calculate roughness length from the wave, but also we modify the wind by wind momentum equation and energy equation by putting the wave related terms. And there are some kind of challenge here also in terms of the pressure correlation term. And regarding to the other question you raised on these LES kind of the wake approach, and also we are using here the actuator disk model with rotation in our kind of simulation that I showed to you. And the last question regarding to assessing the LES in different kind of varying conditions. Yes, we have done very intensive standalone kind of PALM, but regarding to these PALM coupled with Worf, we just did these simulations that I have shown, and because we have just finished the first round of verification for this scenario, but we need to explore further these coupled nested system later on. But in the standalone, yes, we have done many kind of experiments covering different varying atmospheric stability conditions and also different heating and cooling kind of conditions. Yeah, thanks for the question.
Thank you, Mostafa.
Yeah, my pleasure. Yeah.
Thank you.
So anything further from anybody else? So we have time for some discussion. So what you have seen at the moment is the design of wind farms as presented by EDF, the mesoscale and ASC coupling from University of Bergen, and the use of surrogate models for loads and also towards life prediction from you that Nicolay presented. Moving forward, we are also working on more with floating wind turbines and also with predicting life on components, not only structures but also on components such as the main bearing or gearbox bearings, which we have started the work, but we will have more results to present from next year. But if I ask an open question, I mean, for load simulations that you've seen today, how many of you in the call who are outside of this project do you use results from, for example, from LES or from measurements directly in your load simulations? I mean, is that something that is a practice in industry or in your institutes today, or do you tend to rely on standalone wind simulators that are provided by different software? I think here one of the things that we are seeing as something very realistic to capture is that all these effects that we see from the air-sea interactions and sudden passages of different fronts, we are able to integrate into our wind inflow simulator and feed it into the wind farm so that we can actually simulate realistic conditions. So if you have examples of frontal passage or other situations that you have seen in existing wind farms that perhaps you're not able to analyze, or you would like to have more inputs on, then you're welcome to contact us, and then we can see how we could how the project results could help you in those situations. Okay, so I think one last any last message from anybody here, if you would like to have any further questions, let me know. Otherwise, this event has been recorded, and you should also be able to get the presentations from people of this, so that if in case some of you missed some of the presentations, then you can read them at your leisure. So if there's nothing further from anyone, then thank you very much for attending this webinar and staying through the full presentations, and we wish you a good evening and good weekend.
Yeah, thanks a lot.
Thanks. Thank you. Bye-bye.
Thank you.
Bye-bye.
Thank you. Bye.
Bye.
Thanks, Mike.
Thank you.
Bye-bye.
Thank you.